Kia ora whānau, welcome to another online tutorial. A bit of an experimental one today where we are playing around with a different format. Purchased an iPad Pro, don't quite have a pencil yet, so we'll be drawing a lot with my finger, so bear with me with any quality issues. Yeah, let's get to it. We are going to be using the Angular Mechanics NCEA question 2018 number 2 A to D. Today, looking through at how to answer these questions. So when we look at the scenario, whether satellites can be launched into orbits that circle around the North and South Pole, this enables the station or the satellite's camera to view the whole Earth or the whole Earth's surface as Earth spins underneath it. The orbital period of a typical weather satellite is 101 minutes. So for question A, they want us to show that in order to keep the camera pointed towards the Earth's surface, right, so to have a stable orbit, the satellite must spin at an angular velocity of 1.04 times 10 to the negative 3 rads per second. Okay, and so we're going to prove that. Having a little think, all right, we've been given the period, we're going to turn that into seconds. So starting off, we're going to get rid of this, and we'll say T, that's torque. T equals 101 minutes, and we're going to times this by 60 seconds in a minute, and we should roughly get 6,000, and not roughly, we get exactly 6,060 meters. Oh, seconds, sorry, oops-a-daisy. Seconds, okay. From that, we know that the angular velocity is equated to 2 pi over t, our period, and from that we can calculate our answer. And if we plug in the numbers, 2 pi divided by our period of 6,060, we get the answer 1 point, make sure that's on there, yep, 368 times 10 to the negative 3, and our units here would be rads per second. Okay, now we look at the numbers that we've used, and we're going to round it to 3 significant figures, and we will get our answer for A as 1.04. Try to make it a bit bigger. 0.04 rad per second. Cool. So that's A done. Now, if we look at B, it asks us to explain why 2 thrusters must be used rather than simply one on one side of the satellite with double the thrust force. Okay, so let's get rid of that. And I'm going to draw 2 scenarios here. And remember, I'm drawing my finger, so give me some slack here. Okay, I'm going to draw a booster with double the force here, and a second satellite on this side, alternatively with 2 smaller thrusters with equivalent forces, okay, smaller than the one on the left. Now, if we were to imagine the center of the mass right in the center of our satellites, would be generating quite a lot of torque. Now, for our one on the left here, we would have a distance between the thrust vector and the center of mass and a force applied, okay, and an equal and opposite reaction from that force pushing us forward. Now, this section here would produce torque, and we would get a anti-clockwise rotation, meaning that if we just had the one thruster, our poor satellite would spin off crazily. Okay, whereas with our 2 thruster scenario, if we look here, okay, we have an environment in which our torques produced are going to be additive, but the forces are going to cancel. Okay, so for pure rotational acceleration, there's a requirement that our torques be additive, that the push from these 2 motors are in the same direction, but the forces applied about the center to rotate them cancel each other. Okay, For this to occur, there needs to be two thrusters whose forces cancel by acting in opposite directions, but whose forces or torques add, as we've seen here. One thruster would only result in an unbalanced force, as we've seen here, okay, and would change the motion of the center of mass, taking the satellite off course, and it would no longer be looking at the Earth's surface. It wouldn't be suitable. Cool. So that's B. We are going to move on to C. The thrusters are fired for 6.48 times 10 to the 3 seconds to set the satellite rotating at the required angular velocity. Show that the rotational of the inertia of the satellite is 50 kilograms meters squared. Okay, so we're going to do that now. We are going to quickly clear the field in terms of our working. We've got through this. I'll chop up to the bigger size. Get rid of all this because we're going to use a lot of space, as I don't have that pencil and rather clunky using my fingers. So we want to find the angular acceleration. Before we can do that, we need to find, we want to find the inertia. Before we do that, we need the period and we need the angular acceleration. Before we have angular acceleration, we need to find our angular velocity. So we're going to start off with that. So we're going to put in the equation our angular velocity final equals our angular velocity initial plus acceleration and change in time. Okay. Now we know in our scenario here, where the thrusters are fired for a short period, rotating at the required angular velocity, and we're going to calculate the initial, that the initial angular velocity is going to be 0. So we're going to put that in. Equals 0. And that's for our initial value. So with that in mind, we can rearrange our equation a little bit here and put in the equation. Our acceleration is going to equal our final over our change in time. Now these are values we have because we calculated them in the previous question, and I'm going to use the unrounded values. So I've got my 1.0368 times 10 to the negative 3 for the rotational velocity we calculated in A. Okay, and again I've used the unrounded value here. You can use either. I just like to use the unrounded values and round at the end to calculate my uncertainty. So I'm going to get that over our period, which we've rounded, and we're going to use delta t, which they've given us, which is 6.48 times 10 to the negative 3 seconds. From that, we get our angular acceleration of 0.160 rads per second squared. Okay. Now, with that, we could use our rounded number, and we probably get a very similar, if not the same answer, because of the significant figures we've rounded to here. So we know in a previous question we talked about there being two torques in the same direction. Okay, we're going to use a little bit of calculation here. We're going to say that, the equation for torque equals force times distance, and we've got two torques. Okay, so we're going to say our torque equals 2 times 5, and we're using our thrusters, which have been given 5 newtons of force, and our satellite's diameter is 1.60. Assuming a central distribution of mass or an even distribution of mass, we know our distance between those two, we're going to be half of that, so we're going to say times 0.8 meters. Right, and for that we will calculate our torque, which will be 8.00, but I'm running out of space here, Newton meters. Now, with that, we can use the equation torque equals our rotational inertia times our angular acceleration. All right. With that, we can rearrange the equation. Our rotational inertia equals our torque over angular acceleration. From that, we can put in the numbers that we've calculated previously, our 8.00 over our angular acceleration of 0.16 from our previous two calculations, and we get our answer of 50.0, and our units for this would be kilogram meters squared. Cool. So that's C. We used our understanding of angular mechanics, velocity and acceleration to calculate our acceleration, and then use that to calculate our torque. Using the information provided from the question, we used both our acceleration and our torque to calculate our rotational inertia at 50.0 kilogram meters squared. Okay. With that, we're going to make a start on question D. All right. So let me just get rid of the working here. And again, once I get my Apple Pencil, this will be a lot smoother and a lot more clean. So looking at question D, it says the radius of a wheel, I missed a little bit here. Instead of using two thrusters to adjust the angular velocity of a satellite, it is often preferable to use a reaction wheel system. Okay, reaction wheels being wheels that spin and use their rotational inertia to control the rotation of an object. When a wheel begins to turn in one direction, the satellite will turn in the opposite direction. The wheel is solid and has a rotational inertia given by the equation I equals 1 over 2 mr squared. Okay, so the radius of the wheel is 0.200 meters and the mass of the wheel is 5 kilograms. Calculate the angular velocity of the wheel required to keep the camera pointed at the earth. State any assumptions. Okay, so we're going to use the equation provided. I'll get rid of this, which is, and I might just thicken the pen up a little bit. Our rotational inertia equals 1 over 2 mr squared. Okay, and we can put in the information that we have from that, which is equals 1 over 2 times our mass, 5 kilograms, 5.00, times our radius squared, which is 0.200. Okay, and that will give us our rotational inertia, which is 0.100 kilograms meter squared. Okay, now we want to use our equation that our angular momentum L equals our rotational inertia I times our rotational velocity, or angular velocity, W. Now we can plug in the numbers that we've calculated or we've got in our previous calculations, and we will get L equals 50.0 times, and again I'm using the unrounded number, 1.0368 times 10 to the negative 3, and that would be equaling 0.518 and we do multiplication here, so our units add together. Kilogram meters squared, radians per second. Okay, and that is our angular momentum. And our main idea here is that there are no external forces acting on the satellite as angular momentum is conserved. We know it's a closed system. There's no other forces, no torque being produced, nothing acting on the satellite. So we can do this equation. Cool. So hopefully you can use this to get out there, get into it, and try some relevant questions. Again, sorry for the chubby finger writing. Hopefully I have my Apple Pen soon. Be a bit more precise with our working. Hopefully that helps. I definitely recommend trying some relevant NCEA questions and using this as a guide to go through. Don't just do this one. Try a different one. That way, if you get the questions right, you're not just copying the working. Good luck.